Okay, so welcome back. We are going to continue discussion of electrostatics, chapter 3 from Zangwill. And here is the rough plan for today. So we'll just do, as a warm-up, one calculation of the electric field through direct integration. That is, not used very commonly, except in situations where the integration is actually, simple enough, trivial. In most cases, you have boundary conditions, and so you actually have to treat the problem slightly differently, and we will look at that with the help of the concept of scalar potential, and then converting the Gauss's law in the differential form into Poisson's equation. Then if we are introducing a new quantity, we need matching conditions for it. One other important property of the scalar potential is that it follows this so-called Earnshaw's theorem. So we'll take a look at that and how it relates to the boundary value problems. And then we will just take a look at maybe towards the end, very simple examples of Gauss's law in the integral form. Okay, so let's get started. The first one is the first problem is actually very straightforward. It's not anything new. It is discussed in the book also, so I won't be going through all of the steps. We won't be focusing on the integration itself. We're just going to focus on the methods that we're using. So let's actually draw a little diagram. So that's a ring charge. And now I'm turning things around a little bit so that we can compare to the discussion we had in the previous class about it. Right? So this is now the z-axis is here. That's x. Sorry, let's turn this around. It needs to be a right-handed coordinate system. So x has to be up, y has to be down. And it's a ring charge, right? So we need to understand that it's not a disk. And for a ring charge, we need, let's take again two elements, one up and one down. And then we all understood this to have the direction of the electric field to be along the z direction, right? And so we know that if we are looking at electric field only in the region of z greater than 0, right? So let's say we're trying to find electric field at this point here. Now let's use that would be the vector that connects let's do this again. Okay, and then we will have another vector showing the direction of the electric field for a, coming from the small element of charge from at the top of the ring. So that's how it's going to look like. And then to figure out the actual components, you need to take, let's say, the component of E along the z direction. And let me get the z axis extended all the way here. There we go. And the z is, okay, so everybody with me so far? Right, that's straightforward. We're just going to now use the Coulomb's law to figure this thing out. So it's going to be now E ring due to the line charge. So since it's a line charge, it's going to be and line integral lambda dl, right? So you will, let's say the line charge is uniform ring charge of uniform density. So you can calculate actually the density to be the total charge Q on it divided by 2 pi r, right? So that's the perimeter of the ring. So anybody, you want to help me write this down? It would be a line integral. So the lambda would come out because it's uniform, and then you would have dl. What should go in here now in the rest of this stuff? Any thoughts anybody has?
What's R minus?
Okay, so let me point out first what is going on here, right? So this is r, right? And the coordinate of this point is some value z, right? It's r is z hat, right? So what's the distance coordinate, right? Remember, it's always 1 over distance squared. So what's the distance that we need to worry about? Looking at the diagram there. Distance, we are trying to only find the electric field due to the two line elements that we have talked about so far, right? And so that's going to be, anybody?
Cos alpha.
Okay, y cos alpha. So let's write down cos alpha, but we will see y right in a minute. But I'm just only looking for the distance part right now. What would that be?
Would that be the square root of r squared plus z squared?
Square root of r squared plus z squared y square root. Remember Coulomb's law is 1 over distance squared, right?
Yeah.
And so you need r squared plus z squared is going to give you the blue here, right? So that's the distance. Right, and so that's what it is. Okay, so that's good. The distance part is good. Why do we have cosine alpha? Anybody? It's a vector, right? So it's going to be in the z direction. We already saw that it's in the z direction. Phi cosine alpha.
Is the Z part.
That's the z component, right? That's a component parallel to the z axis because the perpendicular components of this, which I'm going to use, let's say a dashed line for that. So the perpendicular component would cancel, right? And then the parallel component, I'm just kind of drawing them to be slightly shifted from each other, but they're basically going to add up. And so that's you can achieve that by doing the cosine alpha. Okay, now does that add everything that we needed? Okay, so now let's take cosine alpha. We can write it down in terms of the properties of the triangle. So cosine alpha is going to be z over square root of, right, z over the diagonal, which is the square root of z squared plus r squared, right? And so we take all of this, substitute it in there, and then we are going to get the E ring. So I'm going to now just write it from here. E ring for z greater than 0 is going to be now lambda over 4 pi epsilon 0 integral dl c hat over, let's not write it down as the square root. We have 1 full power of z squared plus r squared and another half power, right? And so that's just going to be z squared plus r squared over 3 halves, right? And that integral can be handled. In fact, that integral is constant throughout the whole length of the ring charge. The distance doesn't change. Everything in that integrand is constant. So all that you have to do is perform the integral dl. So it's very, very easy integral to do. And only in those cases you actually use Coulomb's law. Otherwise, you don't fiddle with Coulomb's law that much. You want to use something else, which may be Gauss's law, or it may be the boundary value problems for the potential. So I'm going to write here as z c hat. Actually, let me do one more thing here. I'm going to write down 2 pi r over 1. That's my integral dl, right? It's going to give me that. And then you will have z c hat over c squared plus r squared raised to the power 3/2. And all of that is in the z direction, right? So everything is okay. This you can kind of see. Let me put a little dashed oval around this part. Lambda times 2 pi r is going to be q, right? Everybody agrees, hopefully. And so what we get essentially is, sorry, I don't want to be writing it like that. What we get here is q over 4 pi epsilon 0 c hat over z squared plus r squared raised to 3/2. Okay, so it just depends on the total charge. Essentially, because of the symmetry, right? You want to, in some sense, you always will have that, but it's not just the. So you could think of this as not just if you thought that whole ring had the charge of q, this expression for intermediate values of z does not quite look like the Coulomb's law, right? It's not quite just 1 over the distance, which is z squared plus r squared squared, right? There is this extra z coming into picture, right? So you need to be careful. It's not always just that. But if you take the limits will have to follow the properties that we are familiar with. So this one now you have to tell me the limits as z goes to 0. That means you have the ring charge and the observation point is very close to the ring, right? What would be the electric field in that situation? Electric field?
0.
0.
Would be 0, right? Because you are at the center. And so everything is radially away from that point. But for each electric field line that's going away on the top side, there would be bottom. And then so there is always a cancellation going on. And so there the electric field will be 0. What will happen if we go to z going to infinity? What would be the limit in that case? So again, you're moving really far away from the charge. And so it will also go to 0. Right? So both of those are sort of straightforward. But we could think of another limit, which is kind of intermediate, where z is much, much larger than r. Okay, now let's calculate that. Z is much, much larger than r. Okay, so let's see what happens in that case. How would we deal with that? Anybody? So let's write down the whole expression q over. So what we need to do basically is limit of, let's say, z r over z
Over squared.
going to 0, right? That's kind of would be the limit because r is much smaller compared to z. And so we just have to write down everything so that the ratio. So I divide the numerator and denominator by z, both of them, and that's not going to cause any problem. So z hat direction doesn't change, divided by the 3/2 power actually makes things a bit more complicated. Sorry, what did I do here? Okay. What I'm going to do is divide the numerator and denominator by, let's say, c to the power 3/2, right? So I do z divided by z to the power 3 halves. And then when I divide that in the denominator, once the 3 halves, z goes inside, I'm going to basically have, actually I need to divide by z to the power 3, not z half. Okay, so when I divide by z to the power 3, when it goes inside the 3 halves part, it's going to become z squared. And so the first term will be z squared over z squared, and the next term would be r squared over z squared to the power 3 halves. Everybody with me so far? Does that make sense? So what we did was divide the numerator and denominator by z cubed, okay, and that just helps us take care of this. So then it becomes, the limit will be 4 pi epsilon 0. We can apply the limit now. So the denominator will basically just become 1. So z over z cubed, which is essentially just z squared, 1 over z squared, z hat. And that is everybody happy with that? Why? Because that looks like Coulomb's law, right?
Yeah.
Because it has the right kind of behavior. It's as if when you're far away from the charge distribution, all of that charge is situated at the center, right? And so that's kind of what you see there. And we don't need to be worrying about. Okay, and so those limits are important. And so in this class, we're going to be looking at limiting behavior of different things. The next application is field due to a disk.
Change.
And you can think of disk as small rings, multiple rings. You so add them all together. So it's very, very simple. So E disk, again, at points that are z greater than 0, so above that axis. So let's think about that disk as like this. But now I'm going to shade this whole thing because the charge is now situated everywhere in that shaded area. And let's say the center is somewhere here. You could think of the disk as being divided into rings of small radius, let's say r, and a thickness dr. It's a standard integration techniques. And so what we need to do here is we just take the expression that we had for the ring electric field and integrate it for the different values of the rings from various radii starting with 0 to r. So it's the radius that's going to change now. So you're going to do integral 0 to r dr. And we are going to take a look at this expression here. We had 2 pi r lambda, right? And so that's what we are going to write down there. Z over 4 pi epsilon 0. That part just is constant, so it just comes out. The charge, and because it's now a disk, we are going to take the charge density. To be sigma, so we don't write it as a line charge density at all. And so the total charge on the ring, which is lambda times 2 pi r, is what we need, which is going to be, in this case, 2 pi little r times sigma. So that's the total charge divided by c squared plus r squared raised to 3 halves. So that capital R that we had for a given ring, now we just turned it into little r with the additional to make it as an integration variable, and then the r can vary from 0 to capital R, and that's how that works. Again, this integral is also straightforward and trivial. You can calculate that. It's one of the standard integrals, and so by doing that. I'm not going to go through the process of evaluating the integral. You're just going to get c over z squared plus r squared square root times c hat. Okay. Everybody with me so far? Makes sense? Again, we need to make sure the limiting behavior is what it should be, right? So let's take a look at now. We're going to take a look at limit c going to 0 plus. That means you are on the positive z side and you're coming to the center of the disk. What do you think will happen to the electric field in this case? Now you're coming closer. In the previous case for the ring, when you went to the center of the ring, they were always balancing charged elements, which would cancel the electric field. Do you think the electric field will be 0 in this case?
Sigma by twice epsilon naught.
Right, because as z goes to 0, the second term becomes smaller, right? And compared to 1, right? So you get 2 O sigma over 2 epsilon 0 z hat. And this is actually similar to the electric field due to an infinite plane. Right, so there is some similarity between those two. What if you come to the disk from the wrong side, right? So from the negative side, or from the other side, what do you think will happen in that case? C going to negative. It's just that the direction is z hat, right? So the direction in that case would be negative z hat, which you can write it as negative 2 sigma 0 z hat. So all that is going to change is the direction. The electric field is always for a positive sigma, the electric field is along the z direction, which is pointed away from the charge distribution. So it would be negative for the, oh, sorry, I made a mistake here. This should be 0 minus. That means you're coming to z equal to 0 from the other side. And then we are also assuming here, of course, r is much larger than c, is essentially what's happening in that case. And so you can ignore the second term, can be ignored actually, because you can assume r is much larger than c. And then you can also calculate the limit of r going to or r much smaller than z. That means you're really far away from it. But again, at finite z values, z is not going to infinity. In that case, the electric field is going to be, any thoughts anybody has? You can divide by z, and so that makes it 1 plus r squared over z. And so it's just going to be z squared. So sigma over 2 epsilon into 1 minus 1 over z. One r squared over, I'm just trying to do the calculation quickly in my head. You're dividing by z. It's actually, I'm going to leave this as a question mark, right? So is this correct? You can verify that later. I don't think that's correct, but you can verify, you can check that later and write down the correct expression. So I'm going to put a question mark there. Yeah, let's not spend time on that right now. That gives you an idea. And then once you figure this out, you can actually take a look at the limit z going to infinity. In that limit, the electric field, actually you don't really need to worry about this thing here because it's a finite plate. So it's going to go to 0. The important thing is, if we make the plane infinite, right? Which is equivalent to what we said here. If the radius of the disk is much larger than the value z at which you're trying to find the electric field, that is equivalent to saying that the plane is infinite, right? Which is what we say, that the answer is similar to infinite plane. And that allows you to determine, for example, electric field due to a combination of two infinite planes. So you have one infinite plane here, which has the charge density, let's say positive sigma. And then you do the same thing with another plane that is situated close by, but has charge density, let's say negative sigma. And what I'm going to do, actually, I should have used different colors for this. So I'm going to use the top one. I'm going to use a different color for it so that we can distinguish between the electric field due to the two different. So that is positive sigma. So what would the electric field look like due to that positive sigma plate, above the plate and below the plate? Anybody? Above the plate, it will be, so think of your z-axis as going through these two plates and it's perpendicular. So above the plane, it's going to be directed. I'm only going to draw the lines because that's how the electric field will be along the normal. But what is the direction? I need to know the direction from one of you. So above the sigma plus plane, what's the direction? Up or down?
Up.
Up. Okay. So up, up. And remember, we're assuming these planes to be of infinite extent. So the magnitude of the electric vector is the same everywhere. So we don't have to worry about that. And so naturally then below the plane, it will be away, it will be down, away from the plane. Now let's take a look at the electric field due to the negative sigma. Remember, now it's negative sigma, so the direction will be reversed. And so in between the planes, it's going to be, now the direction would be directed towards the plate. And so between the plates, both the electric fields are adding, and in the region outside of these plates, the electric field components from the two plates are opposite to each other. Remember, the distance doesn't matter. Even though you're farther away, when you are below the negative sigma plate, the magnitude of both the electric fields is zero. I mean, magnitude of both the electric fields is exactly the same. And so because of the opposite direction, this is going to imply that E is equal to zero here. That's going to imply that E equal to zero there. And E here is going to be E from the plus sigma plus E from the negative sigma. And so they just add together, which is going to give you sigma over epsilon zero C hat in the positive direction. Okay, everybody with me so far? Makes sense, right? That is the capacitor. Because for the capacitor plates, there is no field that leaks through the capacitor plates. There is electric field only in between the two plates. And we can use that, of course, for storing charges and such in the electrical circuits. Another thing to note here is any real capacitor would, of course, would not have infinite charges. But at the center of the capacitor, this is a good enough approximation for determining the electric field. As you come closer to the boundaries, then the electric field lines will not be like they are shown here. There would be a little bit of a curving happening around the edges, right? And so that curving is something that we're not going to, you will have to calculate that very carefully, specifically if you needed to do that. But we're not going to worry about that just yet. The best way to deal with that is through the boundary value problems. And so then in the previous class, we talked about through the application of Helmholtz theorem, we could see that the electric field can be written as negative gradient of some quantity that a scalar to begin with, right? And so this is the origin of the scalar potential. And it is completely dependent on the nature of Coulomb's law, right? Because it's 1/r². Let me actually take you there. So we can just take a look at where we introduced it, right? So here, that's the potential. So we can write it as negative gradient of this Coulomb type integral, but now you don't have 1/distance squared in the denominator, you just have 1/distance r minus r prime, right? And so that is a scalar quantity. Now, the thing with the scalar potential is its actual absolute value is not important. What we care in any physical situation, what's going to be important that it has the right kind of derivative. And that means the reference point where phi of r is equal to 0, let's say phi of r0 is 0, is fully arbitrary. You can choose, according to your convenience, where you want the potential 0 point to be. Without that, you have that freedom basically, because it's only the gradient that has to be accurate, and physically meaningful quantity is the electric field. Electric field is what you're going to be measuring when you put a test charge in the region. You can never measure the scalar potential. It doesn't have any absolute value. Its absolute value does not make sense, right? Everybody with me so far? So it's only the potential differences that are important. Potential difference is a physically meaningful quantity, not the value itself. Okay, so potential difference is physically meaningful, potentials themselves are not, right? So that's that. Once you have that, you can then, based on the expression that we saw last time, if you have volume charge, then you can write down the scalar potential to be through the Coulomb integral of r minus r prime. Now, why would we worry about the scalar potential if it has such weird properties? It's because it's a scalar potential. You don't have to do as much work as you would have to do in the determination of the electric field directly through the integral. The example that we saw is actually very simple, where the integration was trivial. You may not have that all the time. Plus, you have to worry about the vector nature. So that means you have to determine all of the components of the electric field, which is not always the easy thing to do. And so you determine the scalar potential through a corresponding integral. So we saw this is the volume case, volume charge density. You have a surface charge density. And if you have a line charge density, then it's just going to be dl lambda of L divided by R minus L. And that gives you that. And in all cases, electric field then can be readily determined through the gradient of the scalar field. And calculating the gradient, of course, is a whole lot easier than evaluating the integral, right? But again, this is not really the end of electrostatics, if you will. Just knowing these expressions is they are formally correct always, but doing those integrals is almost always going to be complicated and problematic. And so you don't want to always rely on doing the integrals. What you want to do is instead convert those into differential equations, and differential equations are a whole lot easier to solve because of all the techniques that we are familiar with. And so instead, what we use is an alternate method, or more powerful, or not or and more powerful, and powerful in the sense that it allows you to address different kind of situations that you would not be able to do through direct integration, is to use Gauss's law. Okay, and so what we do is we have the divergence of E equal to rho over epsilon 0, right? That you can convert into divergence of the negative gradient of phi, that is going to be equal to rho over epsilon 0. And then when you take the divergence of the negative gradient, it's going to give us the Poisson's equations. Del squared of phi of r is going to be negative rho over epsilon 0. I'm just going to put this in the box. Okay, so that's called Poisson's equation. Again, Poisson's equation is an inhomogeneous second order differential equation in 3D coordinates space, whichever you want to take, Cartesian, cylindrical, or spherical. So it's not always directly solvable by itself. What you want to do first is convert that into Laplace's equation. So turn the right-hand side to be equal to 0. And once you have the solution for the Laplace's equation, you look for particular solutions to the homogeneous part, and then you add them together, and that gives you the solutions to the Poisson's equation. Now, compared to the standard methods that we looked at in the mathematical physics class, the challenge in solving Poisson's equations is the boundary values, right? You need to get a specific solution, you need the at least two boundary conditions, so to speak, right? And so these are called then the boundary value problems. In electrostatics. So there are two methods for dealing with, or determining electric and let's just say for now electric fields when somebody gave you a charge distribution. And one of the methods is direct integration, which is essentially using superposition principle, or the second method is through the boundary value problems. And we will take a look at this one from the chapter 5 onwards. Right now, we're just looking at the first method, which is direct integration. But can we make that effort a little bit easier for us to handle, right? And one of the ideas is, so again, going back, we kind of digressed a little bit and talked about the alternate method, but we're not going to go through the details just yet. Recalling a few other direct integration methods. We are going to look at the integral form of the Gauss's law. Anybody remembers how it looks like? because that takes care of a whole class of problems like you see in this image here, right? So if you have a spherically symmetric charge distribution like in picture A, or a cylindrically symmetric charge distribution in B, and then in a plane, which is like the Cartesian charge distribution, like in part C, the dashed lines form so-called Gaussian surface. So anybody remembers the integral form of the Gauss's law? Who wants to help me here? You have seen it before. Okay, let's take the differential form and see if we can turn that around, right? So divergence of E equal to rho over epsilon 0. And let's take a volume integral on both sides, right? So if you take the volume integral, divergence of E t cube r is going to be rho t cube r over epsilon 0, right? And epsilon 0 you can of course take out. So I'm going to move epsilon 0 to the other side. So you get divergence of E t cube r is equal to integral rho t cube r. So it's essentially just becomes the total charge in a given volume, right? So the volume is given, volume is fixed, essentially. So what can we do? Anybody remembers a technique to manipulate the left-hand side? So-called divergence theorem, right? So what does divergence of E give you? It gives you these electric field lines that are going out a given volume. You take a look at the boundary of that volume, and all you have to calculate is the flux of the electric field passing through those boundary points. And so this becomes a surface integral of E dotted with the normal vector to the boundary of that the volume, and it becomes now a surface integral and hat ds. And epsilon 0 is still there. You haven't done anything with this, and this just gives you the total volume charge, QV, right? So the charge contained in that volume. Everybody with me so far? So if you don't remember the integral form of the Gauss's law, here's how you can quickly arrive at it by using the differential form. And these kinds of manipulation techniques, you want to be able to be comfortable with them because they allow you to go from one form to the other. So we are coming back again to the superposition principle and the integral form. But this integral form actually becomes a whole lot easier to handle if you have symmetry, right? So useful if one has symmetric charge distributions. Right, so why? So take a look at the diagrams here. In A, for example, the 3D spherical coordinate that you have r, theta, and phi, but the charge distribution has no dependence on theta and phi. That means it is spherically symmetric. It does not depend on theta and phi. Plus, if it is uniform, then it doesn't even have r dependence, right? And so you can take a look at that to be same idea works for B and C. Also in C, it's the XY plane where the charge is. It's independent of Z. In B, the cylindrical charge distribution, it's independent of the theta coordinates, and it's independent of the Z coordinates. So those kinds of things make up the surface integral evaluation extremely easy. And so you don't have to do Coulomb integration. This is a next level technique, but it helps if you have symmetry. And so I'm sure in your undergraduate E&M classes, you have solved many Gauss's law based electric field determination problems. So I'm not going to go through the process. You can see the Gaussian surfaces is your first step, and those are shown here in the diagram. And then you go through break that surface into small elements, and essentially that surface integral gets split into. So in the case of spherical, it's just one surface. For the part B, there would be the end caps would have to be evaluated differently from the cylindrical surface, and so on. But you can do these integrals, and that's another sort of review of the techniques that you're familiar with, and we're not going to do that. You can use, for example, the picture C to determine the electric field due to an infinite plane. That's another method of doing that. So that is something that I'm going to leave you to deal with later, because you know how to handle that part. Okay. Any questions anybody has at this point? Let me quickly look at the set of topics that we were going to discuss today. So we did the direct integration. We looked at the scalar potential and Poisson's equation and introduced that. We have looked at Gauss's law in the integral form. Let's now look at matching conditions for the scalar potential and the Earnshaw's theorem for the boundary value problems. Okay, so there are two things that we need to discuss still before we go into the so give me just a second here. Okay, so let's first now look at the matching conditions for phi of R, and you know the matching conditions for the electric field. So we can actually use those to figure this out. So recall that E perpendicular is discontinuous. Right? And again, we kind of make our life easy by assuming it's a simple plane. But if you go from a flat plane to a curved plane, all that happens is the equations have to be applied separately at each point. That's all that changes. Other than that, it's fine. And E parallel is continuous. Okay. And so what you basically have is, right, so that's 1 and 2. Let's write down the mathematical expression for 1, which is n2 hat dotted with E2 minus E1 is going to be equal to the charge density on that surface and sigma. So let's actually maybe just draw a quick diagram. Okay, so that's our surface. Let's take this to be region 1, region 2, and 2 would be there, and 1 would be in this side, and then you can write down the other things. Okay, so we have this. How do we get this? E now is negative gradient of phi. So let's, sorry, phi is not a vector quantity. Gradient is. So let's take this, substitute in that equation, you get n2 dotted with negative gradient of phi 1. So we now have, here E1, phi 1 in that region, and E2, phi 2 in this region. Okay, so negative gradient of phi 2 minus negative gradient of phi 1 is going to be equal to sigma over epsilon 0. And can anybody tell me what this thing is going to look like? Well, let's adjust the signs here. So you get or let's leave the signs as they are because the negative sign is important. Okay, because you want the n2 terms to come first. So let's look at consider n2 dotted with negative gradient of phi 2. What is that? Can anybody tell me what this is?
Q.
So you have gradient of phi 2, right? You have a certain direction for the gradient, right? But you are trying to take, so this is a vector and you're trying to look at its projection along the n2 direction. What does that give you?
It should be a gradient. It should be scalar, but in the end,
so let's think about this. If I have, right, so gradient of phi, let's take a look at it in the Cartesian coordinates. X hat partial of phi with respect to x plus y hat partial of phi with respect to y plus z hat partial of phi with respect to z. Everybody agrees? Now, if I let's say take x hat dotted with gradient of phi, what does that give me? Forget the negative sign. It's going to give me partial of phi with respect to x. Can we generalize this to say n2 dotted with negative gradient of phi 2 is going to be equal to partial derivative of phi 2 with respect to the coordinate that corresponds to n2. Would you agree with this? Right, just like here, whatever was the unit vector coordinate, that when you take its dot product with the gradient vector, it pulls out the derivative along that direction, right? That's all that means, along that coordinate, partial derivative along that coordinate. Okay, so that's how that is going to be. Right, so this would turn out to be negative sign. In this case, right, because you have the negative sign here. So let's get this expression now and rewrite it. It's going to give you partial of phi 2 with respect to n2 and minus partial of phi 1 with respect to n2. And there is a relative negative sign between them because n2 and n1 are opposite to each other. So that's what these n2 dotted with e2 minus e1 gets transformed into, and you have sigma over epsilon 0. That means what we get here is that the normal derivative of phi is discontinuous across a charged surface. Okay, that's what that means. And the parallel component of the electric field being continuous, that just translates into phi 1 at any position on the surface would have to match in value with the, sorry. So at the surface, phi 1 and phi 2 coming from both the sides, they have to match, right? So that means phi r is continuous through a charge surface. And that is, of course, valid at all points along the space, along the charge density R of S. And even here, you can, strictly speaking, if you add the dependence on the position for both of these or all of these quantities, then it would be a equation that would be general enough that you don't need the flat plane. Any curved plane would satisfy those properties. Okay, everybody with me so far? So those are the matching conditions that you would need to consider, because remember, from the theory side of things, what we have done is we have said dealing with determining electric fields is equivalent to determining the scalar potential. And so if you do scalar potential, you will have these boundaries, and you want to be able to use those to determine the scalar potential fully across the boundary of a charge like that. And so that part kind of takes care of it. Okay, so the next thing that we want to talk about is, yes.
I got lost with the negative sign after we did the
Yeah,
MT.
that I did not deal with those very carefully either, right? So let's take a look at this thing here. If you do, you want me to do it, or this is something you can figure out, right? It's only negative signs, right? You need to carry those forward, and you could figure those out. Okay, so I will leave you to deal with those, and then that's straightforward. This is what you would get in the end. Okay, so you can figure those out. That's not a big deal here. I skipped that part in the interest of time.
Okay.
Okay, now what I want to talk to you about is the Earnshaw's theorem. Give me just a second. Okay. So since we are changing our electric field determination problem from the electric field, first we, the measurable quantity experimentally is the forces. But we said, forces are not always something that you can measure. You're going to have test charges, and if you're going to have essentially, instead of having this action at a distance that the Coulomb's force implies, we went to the field picture that the effect of a charge is there everywhere, and any test charge that you bring into that region experiences that, and so field becomes now kind of a more fundamental quantity that's there everywhere in space. Then we said, okay, the electric field, that's kind of inconvenient. It has three components. I have to do these integrals, not very straightforward. Can I make this thing easier? Instead of trying to do three integrals, can I do just one, which is the scalar potential? And then we looked at the matching conditions. If we have to hop from one region to the other, which are separated by boundaries, that boundaries may have the charges on them. We didn't have to deal with the boundaries with currents, because it does not deal with the scalar potential is not going to be changing. We have constant flow of current that is not changing with time. And so that's why we're not dealing with that. We will have to deal with that when we start talking about similar quantities in the magnetic situation. Now, let's take a look at the Earnshaw's theorem. That provides a sort of a general property of the scalar potential that they have to satisfy always, right? And so here's the statement, and we will just go through a quick proof of that as well. And so that the statement says the scalar potential phi of r in a finite charge-free region of space R, that just means, you have, strictly speaking, it should be that, right? Takes its maximum or minimum values on the boundary of let's just go with what the book had. So I'm just going to call it R so that we can be able to recall it, right? So whatever may be the region, we call it R, just because it has nothing to do with its R3. Even though, it's mathematically, strictly speaking, that's what it is. Okay, so that's what it says. The maxima or minima, remember, this is very, very, very powerful statement. The phi, you don't know anything about phi. In a given region of space, there are no charges, but there may be charges outside that are generating this phi. What you could say is within this region, you cannot have a maxima or a minima of the phi. The maxima or minima will only be on the boundaries, not internally, not inside the volume of interest. So in that sense, it is very powerful. So let's quickly take a look at that. And it actually allows us lots of calculational tools to figure these things out. It allows you to figure out the equipotential surfaces, corresponding electric field lines, when somebody gave you a charge distribution. So we do, the standard mathematical techniques sometimes to find a proof is we assume the contrary and then prove that you have arrived at a contradiction, right? So we say that assume, or let's say we suppose that phi of R has a local minimum at a point P in the region R. That means the gradient vector in a certain direction, remember it has a minimum, right? So minima means from that point of minima, if you try to go away, the derivative is going to increase, right? Derivative will be positive rather. The value is going to increase, derivative will be positive. Okay, so this implies at every point on a tiny closed surface enclosing. Now, since we have to talk about three-dimensional and it's not one-dimensional picture anymore, so point P is located here. If you have a small surface that's enclosing P, right? So a volume that encloses P, but we only deal with the surface. At all points on that surface, the n dotted with gradient of phi would be positive. That means if you take an integral along that whole surface, n dotted with gradient of phi will be positive. Recall that the electric field is negative gradient of phi, and from the divergence theorem. So what this becomes is a volume integral, and so E equal to negative gradient phi and the divergence theorem. And then of course the negative sign. So because of that, we can turn this n dotted with gradient phi to an electric field with a negative sign, and then you do a volume integral of its surface. The flux would become a volume integral once you use the divergence theorem. So you get d cube r rather, d cube r divergence of E So the left-hand side has been turned into a volume integral. The right-hand side was positive, but now because of that negative sign, this is going to be negative. Okay, always. Okay. But we know that divergence of E is equal to rho over epsilon 0, which is going to be equal to 0 because rho is equal to 0 inside the volume V. And so that means we have reached a contradiction. Right? We started with having a minima inside that volume, and we showed that that leads to divergence of E volume integral being negative, whereas it should actually be 0 because there are no charges there. And so we reached a contradiction, and that means we are always going to have the ds n hatted with divergence of phi equal to 0, right? So equal to n, and that translates into phi being phi of r having no local minima or maxima except you can have local minima or maxima only on the boundary, right? Not inside. Okay, so that's how that works. This, of course, is quite powerful. It can be used for a variety of different calculational tools for determining phi of r when we need it. Right? So let's, for example, say that. Let me just quickly see what we have, what we wanted to do. So I think in terms of what plan we had for today, we have covered everything. So I'm just going to stop here and see if you guys have any questions on any of the topics that we discussed today.
Kapale, I think for the sign earlier, I think it's supposed to be the phi1 minus phi2.
Okay, so if that's the case, bring, why don't you write it down and share with us, right? So in the next class, you can do that.
Okay.
Okay, so just show the steps and then we can quickly take a look at it if we have to modify the equation in the book, if there is an error there.
Okay.
Yeah,
I don't think. Yes.
I guess what caused the problem is the way we take the difference of the electric field. If it is E1 minus E2, then it will correspond to what you gave in class. But we started
Right.
with
Let's see. Did I make a mistake? Yeah, I think I made a mistake here.
It should be E1
I made a
minus
mistake. It
So
should be
E1
E1 minus E2.
everything aligned. Yeah.
Yeah. Then everything is okay. Then this would be negative gradient of phi1.
Yeah.
Negative gradient of phi2. And then that would fix the sign problem. Okay, very good, Joanne. That was good. Okay, so I just made correction. Make sure you make those corrections, right? So I made an error when writing this down. It's E1 minus E2 dotted with N2 hat. And then that would correctly translate into all of the different steps, and the negative sign will lead you essentially to this, where the things get reversed. Now it's phi2 minus phi1, right? Or the normal derivative of phi2 minus the normal derivative of phi1. Okay.
Excuse me, doctor.
Any other questions?
Excuse me,
go
doctor.
ahead.
I remember
Yeah.
you said we are delaying the midterm exam. So
Right.
when it will be?
Next Thursday, right? So it was supposed to be today, but it's not. Of course, did not happen today. So it's going to be next Thursday.
All right.
Okay.
In the same manner.
Same manner. Yeah, we will be here in Zoom, and then we will do the test.
All right. Thank you.
Okay. Very good.
Dr. Kapale.